Las leyes de la naturaleza son ineludibles. No existe nada ni nadie que pueda escapar de ellas. Pensemos, por ejemplo, en una de las más importantes, la ley de la gravedad o atracción de los cuerpos. Según esta ley, todos los cuerpos se atraen entre sí con una fuerza que es mayor cuanto mayores sean sus masas y menor la distancia que los separa. Gravedad. No se necesita nada más para ponernos en movimiento. Desviarnos de nuestro camino o desintegrarnos. Bienvenidos al mundo de las leyes de la termodinámica.
One of the main goals of thermodynamics is to describe the transfer of energy. We've already described two processes as a transfer of energy, work and heat, and they're both connected to each other. As a thermodynamic system does work, it loses heat. When work is done on a system, it gains heat. So heat is converted to work, and work is converted to heat. Together, the work and heat transferred into or out of the system represent the change in its internal energy, which, as you might recall, is the total kinetic energy and potential energy of all the molecules in the system. This idea that the change in internal energy is equal to the change in work plus heat is so fundamental that it's known as the first law of thermodynamics. So we can have an equation to use for analysing problems. We write the first law like this. The internal energy, U, of a closed system is equal to Q, the heat transferred to the system, minus W, the work done on or by the system. Now you'll notice that the first law of thermodynamics describes only those two factors, work and heat, as affecting a change in internal energy. That's because as long as the system is closed, meaning it's isolated from the rest of the universe, there just aren't any other factors involved. The amount of heat lost by the system is exactly equal to the amount of work done by the system, and vice versa. So really, the first law of thermodynamics is just another way to describe the conservation of energy, which keeps coming up in our lessons because it's such a key principle of physics. There's always some kind of heat loss, like through friction. Even that tiny amount means that the motion can't continue forever. It will eventually run out of the energy it needs to drive the work it's doing, moving. Now, there are four basic types of processes where the thermodynamic properties of a system, generally an ideal gas in some kind of container, can change according to the first law. In each case, one property is held constant, volume, pressure, temperature, or heat, while the other properties change. Variations on all these properties are used in all kinds of machines, especially engines. First, there are isovolumetric processes where the volume is held constant, usually because the gas is in a rigid container, while heat is added or removed. As you add heat, the pressure of the gas will increase and so will its temperature. As you remove heat, the pressure and temperature would decrease. Isovolumetric processes are kind of boring as thermodynamic processes go. The gas is stuck inside its container, and no matter how much heat you add, the gas doesn't do any work. You're just increasing its internal energy. But isobaric processes, where the pressure is held constant while heat is added or removed, are a little more interesting. Here, the volume of the container is allowed to change, usually because the gas can move a piston. As you add heat, the volume and temperature of the system increase, and as you remove heat, the volume and temperature decrease, which means that an isobaric process can do work. The third type of thermodynamic processes are isothermal. That's where temperature is held constant, usually by connecting the system to a much bigger system whose temperature would take a lot of heat to change, known as a heat reservoir. The heat or volume of a system is then changed very slowly so that the other properties can adjust while the temperature essentially stays constant. An isothermal process is kind of like an isobaric process in that if you add heat, the volume will expand, so the system will do work. Finally, there are adiabatic processes where no heat is allowed to flow in or out of the system, but the gas can expand or be compressed. Again, the equation for the first law of thermodynamics helps us out here. Q is 0 because the heat of the system isn't changing, but the internal energy of the gas can change, so the system can do work or have work done on it. In fact, the change in the internal energy of the gas will be exactly equal to the negative of the work. But this is all just the first law of thermodynamics. There's also the second law, which says that heat will spontaneously flow from something hotter to something colder, but it won't flow from something colder to something hotter. And that's because of this thing called entropy. Entropy is often described as the inherent disorder of a system. The more disordered the system, the higher its entropy. So a gas, for example, with all its molecules randomly bouncing around, has a higher entropy than a solid with its molecules neatly arranged. And a more general way to state the second law of thermodynamics is that in real life, entropy can only increase overall. That doesn't mean that entropy can never decrease in certain situations, like gases do sometimes turn into liquids or solids, obviously. You've seen water vapor condense and liquid water freeze. But if the entropy in a system decreases, that means the entropy of the environment around the system must increase enough to compensate and then some, so that there's an overall increase in the entropy of the universe. Say you put water in your freezer to make ice, for example. The entropy of the water goes down as it freezes. But meanwhile, your freezer is putting out heat as it works to keep itself cold inside. And the heat from your freezer is increasing the entropy of your kitchen more than the entropy of the ice is decreasing. So overall, there's an increase in the entropy of the universe. Remember that. Every time you're making ice, you're increasing the disorder of the universe. Now, entropy's tendency to increase has to do with probability. And in thermodynamics, entropy is related to heat flow because when heat flows between systems, their entropy increases.
Hey guys, now that you guys have reviewed some of this basic concept of the first and second law of thermodynamics, for further understanding, let's head to the lab and let's get some experiments done.
First, break the empty beaker and container. Fill the beaker and container with adequate amount of water. Break the mass of hot water and cool water. Boil the water in the beaker until 18 degrees Celsius. Pour the cool water in the large container. Then, place the beaker of the hot water on the holder in the large container. And finally, place the thermometer. This is to measure the temperature of both cool water and hot water. The temperature recorded until it reached the same temperature, which is called as thermal equilibrium.